Bueno, buenos días a todos. Mi nombre es Claudio Burgos, profesor asistente de la Universidad de O'Higgins, aquí en Rancagua, y les doy la bienvenida a todos a esta cuarta charla de un ciclo de seminarios que se enmarca en el proyecto FOBI 210023, ¿ya? Llamado Microredes Eléctricas para una agricultura energéticamente sustentable. Hoy día con nosotros está el profesor Mark Sumner de la Universidad de Nottingham en Reino Unido. Solo algunos comentarios. Si tienen preguntas durante la presentación, las pueden poner en el chat o al final también las pueden expresársela directamente al profesor, ¿ya? Ahora ahí voy a cambiar a inglés. So now I will switch to English. Hello everyone. Thank you for attending today to this presentation. So for me, it's a pleasure to be here and have Professor Mark Sumner, who is a full professor at the University of Nottingham, particularly in the PMC group at the University of Nottingham. Also, he was one of my supervisors during my PhD studies, so I'm more than glad to be here with him. So, short bio, Professor Mark Sumner received his bachelor degree in electrical and electronic engineering from Leeds University in 1986, and then he worked for Rolls-Royce company in Ansty, UK. Then he moved to the University of Nottingham, where he completed his PhD in induction motor drives in 1990, and after that he worked as a research assistant in 1992. Currently, he is a professor of the electrical energy system. His research interests cover control of power converter, power electronic system, including again power electronics, power quality, stability of power electronic converter, and novel power system for location strategy. So today, Mark is going to give us a talk named "Can Energy Communities Help with the Challenges for Future Electricity Grids?" So Mark, all yours, please go for it.
Thank you, Claudio, for that kind introduction. So the talk today talks about trying to get people to work together with their energy needs as a way of addressing the challenges that electricity grids face in the foreseeable future. So trying to change user behavior, aided a little bit with technology as well. So before I start the presentation, I thought it was worthwhile just providing a bit of background for myself. So I'm from the Power Electronics Machines and Control Group at the University of Nottingham. And if you don't know where Nottingham is in pretty much the centre of the UK. We're about 130 miles north of London. We're quite a small city with a population of about 300,000 within the city centre. And we have two major claims to fame. One is Robin Hood, was based around Nottingham. And the other was that probably 40 years ago now, we had a very famous football manager, Brian Clough, who took Nottingham Forest, our local football team, to become the European champions twice. So Nottingham has not had a Premiership football team for many years, but this season, Nottingham Forest have returned to the Premiership, so we're looking forward to first-class football again, hopefully anyway. So in terms of our research, I'm part of the PEMC research group, and it's a big group comprising of more than 150 researchers who very much focus on all technologies and applications associated with power electronics. So that includes applications for transportation, so automotive, marine, railway, aerospace. It includes applications associated with renewable energy, we have traditionally had a very strong industrial section working on industrial motor drive systems. And obviously we work in the area of smart grid technologies as well. But also underpinning that, we have a lot of work looking at power electronic integration. So looking at making systems smaller, lighter, and more reliable as well. So trying to understand physics of failure and improve health management within power electronic systems. So there's a very wide range of research that we do within the research group. And luckily, we've now got a new research building. We've recently moved into our new Power Electronics Centre on our Jubilee campus, which is a much, much bigger laboratory facility. And also we have room for substantial office space as well. All of the academics are kept here together. And we have some quite substantial experimental facilities with some very large experimental supplies available to us as well. So we're very proud of our new home, and we're doing some interesting work, not only on power electronic systems, but also on looking at a manufacturing of power electronics and motor systems as well. So there's some interesting developments lying ahead for us there. Now, moving on to my area of work, as Claudio has said, I work on power electronics, mainly for grid-connected systems these days. So that includes looking at power quality and stability and grid forming versus grid following converters and that sort of thing down at the lowest level of the control system. But also, I've been working with colleagues looking at what we call community energy, which is where we try to get people to work together to trade energy, peer-to-peer trading, if you like, and see what benefits that can provide to both the end users and also the national grid operator as well. So the background to this, certainly within the UK, and I guess it's very much the same in Chile as well, is that we have had a substantial increase in domestic generation over the last 10 or 15 years, mainly with photovoltaic systems being installed at household level. And this was initially encouraged by feed-in tariffs, but also people wanted to take control of their own power and energy systems as well. So people are starting to install more and more solar panels, and we also have some low-level wind systems as well. And in parallel to this, we've had a massive move towards the electrification of other loading systems. So in the UK, we're starting to see ground source heat pumps, air source heat pumps as a mechanism for heating domestic dwellings, and also an increase in the use of air conditioning systems in the summer. I don't know if you've heard, but in the UK, we have an exceptionally hot summer this year. So it's putting very, very big demands on our electricity system with the air conditioning systems around. And also there's obviously the move to the electrification of transport as well. Not only electric cars, but we're seeing more tram systems in the UK, more electrification of trains and buses as well. So all forms of transport are moving to electrical fed. So this is placing significant challenges at the distribution level, both in terms of, for example, voltage variation, and also in terms of reverse power flow. And this really does present challenges for protection systems and ultimately distribution system management. And there are areas within the UK system where there are significant system bottlenecks. So if you know the topology of the UK, the southwest of England, which is where Cornwall is, and Devon, those are the two main counties in the southwest. They're very sunny counties with fairly small population sizes, no major cities there, reasonably sized cities, but no big cities. And it's a great place to put solar energy generation, but the local loading there does not really balance the generation that could potentially go there, and it's creating problems with the distribution system. And the local network operators have been quite sort of imaginative in trying to solve these problems. So, for example, they tried something called the sunshine tariff, where they made electricity free during the daytime so that any local solar energy that was available could be used locally rather than put back into the main system. On top of this, we know PV prices are reducing, domestic battery prices are reducing as well, and we've got the immediate uptake of second life electric vehicle batteries, I guess, where batteries coming out of automobiles that are 5 or 10 years old need to find another use, and one use potentially is in aiding at distribution level. We're moving towards having electricity systems which can exploit time of use tariff schemes. So that might help to encourage different types of user behavior when it comes to electricity consumption. And with all of these different challenges, the additional PV, the electric vehicle charging, the use of electric trams, the use of electric heating, it's really starting to put pressure on our existing infrastructure and bringing real demands for infrastructure reinforcement. I mean, that's what the picture on the bottom right-hand side is illustrating, that it's, if you want to reinforce distribution systems within cities, it really causes a massive amount of destruction as well. So there's a lot of challenges here, and potentially the idea of community energy can help alleviate some of these problems, defer some of these challenges, and at the same time bring benefits to end users as well. So what is community energy? So what we're doing is defining community energy as a group of neighborhood dwellings, a group of neighboring dwellings that have within their area their own generation, which is usually solar, but it could be other things. We've seen pumped hydro systems available and other hydro systems available as well. And also they might have battery storage systems combined within them. And the idea is that the members of the community are able to trade excess power in a hierarchical way, and that can be done within the community. It can be done within battery systems within the community. So it might be that we have a central battery system, a community battery system, if you like, and that can be used as part of the trading of excess solar energy during the daytime. And if that doesn't work, then we still have connection to the main electricity grid. So I need to reinforce here that the aim is not to operate as an island. We're assuming that the grid, the main grid infrastructure here is available. All we're trying to do is to present ourselves as a community with more of an ideal power flow and see what benefits that gives to everybody involved. So if we're defining that as a community, an energy community, then the question I'm asking really is, can these energy communities help with the challenges of future electric grid systems? So we've had a few projects over recent years, and the aims really of our investigation are to see whether prosumers in an energy community can work cooperatively to help. First and foremost, it's to reduce the electricity costs of the actual community members themselves. So anybody who's willing to participate in an energy community should see an immediate cost benefit, hopefully, for their electricity supply. We also want to improve consumption patterns as seen by the local DNO, effectively peak shaving, if you like. But that also includes trying to consume locally generated energy within the local environment, improving self-consumption, if you like. We want to avoid system bottlenecks to allow more generation to be connected within our distribution system, but at the same time reduce reverse power flow so that we minimize any problems or additional challenges associated with protection systems, and improve local voltage control as well. So all of these things are what we're trying to do in order to improve what is seen by the electricity network operator. And then on top of that, I mean, those are technical challenges and technical understandings that we're trying to develop. But on top of that, we want to see how the community works from a more social economic point of view. So can you gain financially by participating in an energy community? Is there a social benefit to this? Can we do this without requiring any difficult changes in user behavior? Obviously, there's some changes that we would like, which would be beneficial, but we don't want to impose anything in a draconian manner. And we hopefully want to impose as few changes to normal consumption patterns from an end user point of view as possible. So in order to try and illustrate what is possible, we did some work on rule-based controllers within an energy management system. So I'm not going to go into this in great detail, but this gives a picture of an overall hierarchical framework, if you like. And at the lowest end, we have what we call these cells, sorry. And the cell is the local community, if you like. And the cell comprises of all of our community members in this particular community, all of their local generation, so their PV systems. They may have batteries connected in some of their houses. And then we've got access to some of their loads to allow us to do load shifting, whether that's electric vehicles that are plugged into charge, fridges, maybe, heat pumps if they're using heat pumps, like ground source or air source heat pumps, as the mechanism for heating their community. And the idea is that we have a local rule-based controller that controls the net power, the net electrical power drawn by this community, such that it follows a target. And the target is set by a higher level control, which we're calling the community energy profiler. And this profiler works with a little bit more general information. So it's interacting with the DNO, the network operator, who can provide predictions of customer load. They can provide instantaneous market prices. We can work with weather and other forecasting, and we can see what's happening in other local loading clusters. And it's not necessarily just houses like we're illustrating at the bottom. It might be shopping malls. It might be manufacturing plants, industry as well. But all of these inputs are coming in, as well as some feedback from each of these communities. And in essence, the community energy profile is sending down a power profile, which the local community is trying to follow. And let me just try and illustrate that with a simple example. So if we look at the lowest level, or sorry, at the highest level, we've got this hierarchical community energy and power control, which is aiming to make sure that power and voltage quality and stability are maintained down at the lowest distribution level. In order to do that, it's managing load shifting, it's managing batteries, it's managing, if necessary, the curtailment of any local generation. And its aim really is to create a predictable energy resource which can contribute wider benefits to the national transmission and distribution system, and at the same time be user transparent. So if you like, if we look at our community consists of local renewable energy sources, home appliances, potentially some energy storage. We're controlling all of these at the lowest level such that the power delivered from the grid follows a preset profile. And that preset profile is coming from the higher level energy controller. So the simplest way to do this as a starting point is to think of an average power profile. So let's look at this as an example for community energy control. We actually set the power profile to be this green dotted line. This is a constant power level. It is the average power that we predict that that community will draw over the next 24 hours. If we don't have any control on the system, then that particular community will draw the electricity that can be seen with the red pattern. So there's a lot of oscillation in here for two reasons. One is that it's only 2 dwellings, so it's a very, very small community. But also, the community contains a heat pump. And this heat pump has a very oscillatory nature to its behavior. So the red oscillations are very much associated with the control of the thermal comfort levels within these 2 dwellings. Now, what we can particularly see is that during the daytime, we have significant export here. So the community power flow from the red trace is going negative, which is indicating that the PV is being exported to the main grid, which is something that we really want to avoid. We want to try and consume PV energy locally to prevent that causing protection and other problems further on down the distribution system. Now, if we add our control for these 2 dwellings, we get the blue profile. And this shows that we've got some control. So the blue profile is a bit closer to the nice straight line that we're after with the green line. But it's not perfect. It's by no means perfect. And that's because we've only got 2 dwellings here. We've got a very, very small community that does not have many dispatchable resources for us to use. And therefore, there's not much control that we can actually take of this community. But at the same time, we've managed to significantly reduce any export here. So there's very, very little export from the blue line now. So that's a big benefit. And then the peak consumption during the evening time has come down considerably as well. So even though it's not perfect, we've got some significant benefits. Now, if we move to a bigger community, so we've got a community of 30 dwellings here. So again, we've got the profile for one of the house, well, a few of the houses shown in the red when we have no control applied. The green dotted line at 25 kilowatts is the target that we're after. And it's just a straight line at 22 kilowatts. And then the blue line is what we get when we employ our community control. And you can see that the blue line is now very, very close to the green line. There are a few deviations along the way here and here. And we have some significant deviations here, and that's to do with the way that we control our charging and discharging of electric vehicles. So we could make improvements to our algorithm here. But really what I'm trying to show you with these 2 pictures is that the bigger the community you have with a simple rule-based control algorithm, you can control the power drawn by that community over a 24-hour period to match a profile. And that profile is one that you would design for the benefit of the network operator. So the bigger the community, the bigger benefits that you get. I mean, obviously you have to spend more in infrastructure, but again, I'll show you that we have some definite improvements in community size. So for example, you saw that when I was describing the community, I said that we had batteries in there to help us with the load movement and the load shifting and the capture of PV energy. Now, the average battery capacity per dwelling that's required if we have small community sizes is about 8 or 9 kilowatt hours. But as we increase our community size, the average battery size per dwelling required comes right down to about 3.5 kilowatt hours. So we have a significant economy of scale here. So by having a bigger community, we can reduce the average size of battery required per dwelling. And that is a major saving in terms of infrastructure here. So these few results have been showing you the basic principles behind our community energy power control. So we've taken this a bit further and started to look at employing model predictive control within these energy communities. So the aims, again, are to minimize household energy costs and maximize PV self-consumption. We're now moving to having time of use tariffs rather than just a flat energy power target. So we're trying to maximize or minimize energy costs on the basis of having time of use tariffs within our system. So the way that we create our system is to have an upper layer, which is the model predictive control layer, that is focusing on energy scheduling for our system. It makes best economic use of the electrical energy within our system. And then it controls the operation of the lower layer, which again follows a rule-based approach, if you like. So the lower layer is following some fairly simple rules as a real-time controller. And the aim here is to make sure that we can compensate if there are any prediction errors, and we minimize energy wastage, and we smooth the fluctuations in power flow and power exchanges. So we've still got this structural or hierarchical structure to our energy management, but we've introduced model predictive control. It's something a little bit more sophisticated at the higher level. And within that, we can forecast PV, we can use historical data to help us with our control, and we can forecast household consumption profiles. So for one house, if we apply this approach for one house, then we get performance that looks a little bit like this. So this is our household consumption before applying any control. This blue dotted line is our time of use tariff structure. So it's cheap overnight, mid-price during the mornings, there's a peak tariff period in the evening, back down to a medium and then low tariff overnight again. And with this particular scenario for this house, if we look at the solar energy generated by its local panels, then there's plenty of energy there for self-consumption. So actually, if we have a big enough battery system and the ability to do load shedding, what we see is that we can pretty much make the power drawn from the grid zero during the day, with a couple of spikes for various reasons, but pretty much zero during the medium and high tariff periods. And then we have some charging of the battery, so some grid power used to charge the battery at night. So it's a bit of an extreme example for one house. I mean, this is using a fairly large battery system. But in terms of what the benefit to the end user is, the cost of energy for this house, if it uses an economy 7 tariff, which is a 2-price tariff, is £290 a year. If we use a time of use tariff like the one shown with the blue dotted line, that can come down to £255 for the year. If we were to try and do real-time pricing, actually buying into the half-hour real-time pricing market, we actually see that the price goes up. And this is because we've got one house here, and it's difficult, as I said before, it's difficult. There's not enough resources to use here to allow us to follow complex patterns, which is what a real-time pricing tariff looks like. But we can also apply similar principles at community level. So say again that this is just for a house, a single house, but we can apply the same principles at community level. So again, we have community level looking at forecasted consumption, forecasted generation using model predictive control. And then down at the lowest level, we can use a real-time controller to control appliances, control batteries, use local smart meter readings as part of its real-time controlling in order to try and achieve the profiling for energy that we want to achieve. And this is a good example of what happens when we start looking at energy, two-layer community energy management. So again, we have this black profile, which is a typical house profile for consumption with a morning peak and an evening peak. And the red is the solar generation associated with that household. And if we put this into our community system, then we can see that we've got some overnight charging for the battery. But as soon as the tariff period goes outside of the low tariff period, then we come down to zero net grid consumption. We're using our battery stored energy, our locally generated solar energy, and we're using load shifting in order to control the power drawn from the grid to be zero and low cost. You can see here at the end of, that at this point, we've pretty much discharged our battery and used up all of our resources. So we then sort of run out of capability for doing any energy movement for the rest of the day. And this is a good point to make here. We don't want to have our system operating as an island. We are assuming that we have a local, we have a national grid system there that is stable and we can connect to, which means that we don't have to have a big battery that can operate our system as an island at any time. So this looks like it's probably a spring or an autumn day, whereby the battery size is just enough to cover most of the day, but not quite cover all of the day. And probably in winter, we would see this happening a little bit earlier in the daytime. And in summer, we wouldn't see anything like this at all. The battery size would be well capable of supplying the energy for the whole of the day. But when it comes to battery sizing, the battery is sized in order to get the best economic benefit over a whole year. It's not to achieve islanding operation, and it's not to achieve the best operation on any one particular day. So we can operate with centralized battery stores, we can operate with distributed battery stores, we can operate with demand side management. And looking at some of the control, slightly different control algorithms we've seen, we can get significant improvements to, or significant reductions in annual energy cost. Here it's 12 or 13%. Using a battery, or even just using distributed batteries within our system. What is interesting about this is these calculations were made 2 years ago now, and we've seen some massive changes to our electricity pricing. So the cost of electricity at peak time has increased probably by about 70 or 80%. So if we were to redo these calculations with current costs of electricity, I think these percentages would probably go up to 25, maybe even 30%. So that is the cost benefit that we're getting by operating as an energy community, trading PV energy and trading usage of batteries as well. So just two more things to go through. So one is the sizing of a community battery. This one is just very briefly talking about a community battery. I'll talk about this in a little while, but we've actually employed a 1 megawatt hour battery within a real energy community. And the regulations within the UK only allow us to use that battery for dynamic firm frequency response activities. The regulations do not allow us to use it for anything else at the moment, but potentially it could be used to service the capacity market. But actually, ideally, we would want it to provide community energy management service, which is basically what I've talked about within the rest of the presentation. The idea of consumers, prosumers within our energy community using a central battery to capture their PV energy when it's not needed, and then to use it later on in the day when they actually do want it. So this is the ideal performance that we would want from our battery, but these are the two markets that we can buy into at the moment. And we've done some analysis again from 2 years ago that says if we have our 100 kilowatt hour battery, the investment cost for that would be nearly £400,000. And the return on investment over 20 years would be best if we were using it for the dynamic fast frequency response market, because that is the one that is really beneficial at the moment. But it would still be significant if we were using it for capacity market or our community energy scheme, which is what we ideally want to do. And the same thing that I've just said before counts here. These calculations are based on electricity prices from 2 years ago. If we were to redo these calculations now, I suspect that this community energy use of a centralized battery would be significantly higher. So it's starting to become a realistic, cost-effective investment that we can make in terms of improving our energy usage, but also in terms of providing benefits to end users, electricity consumers as a whole. So the last thing I want to talk about briefly is the real energy communities that we've done work with. So we do this for real. We don't just do it as computer MATLAB exercises. So we have an experimental laboratory whereby we have various PV and battery systems, and we've got some PV panels on the roof of this laboratory, so that we can actually make this equipment work in real time and evaluate its behavior in real time in a safe laboratory environment. But then we can go out and we can actually make it communicate with real-time data collection from a housing estate or from other energy sources as well. But we've actually implemented these techniques in 4 different experimental facilities. So the creative energy homes are these 7 houses that we have on Nottingham campus that are lived in by academics and students. And we've put a community energy battery there. That's this thing here. And we ran the system and saw some really good improvements on energy and electricity power profiles there. And then we took it out to Corsham, which is an area in the southwest of England, and put batteries into various different types of housing. So we had 20 houses involved in the experiment. Some were modern like this, some were very old like this one. And there we encountered the real problems associated with trying to do communications. Wireless communication didn't work, so we were having to do power line communication. And we had real challenges in making the communication system work reliably and adequately. But it did, and we were able to demonstrate some of our control algorithms working for real over a period of days and weeks. The Sensible project was a project that was funded by the European Union, and that was for a housing estate in Nottingham, whereby we had 40 houses involved. Did something very similar, and we saw some really exciting results there. And in both of these tests, we were able to talk to the end users and see what they thought about having this technology in their house, and what they thought about having the control taken away for demand side management, and how they interacted with washing machines and dishwashers, their use being moved, or electric vehicle charging being moved. And we gained some valuable insights into consumer behavior. And then the Trent Basin project is actually a live project now, whereby we have this community battery of 1 megawatt hour. We're doing demand side management. We have lots of PV employed within the system, and the electric vehicles within the system as well. And this is the Tesla battery that is part of this system. So what we're demonstrating with this Trent Basin project is putting these technologies into new build housing estates. And one of the key things here is not the technology, that a lot of the technology is off the shelf. It's very commercially mature now. But the things that we're finding exciting are working with the community. So we've set up a community hub for communicating data about energy consumption to to the community residents. But that community hub has expanded to become something more than just for energy. It's about all different aspects of community life. So it's triggered, the energy part of this project has triggered a much, much better community life down at this new housing estate. So we're really proud of that. So coming to my conclusions here, so we've shown that technologically these systems can be put together, and if we can perform clever control algorithms, everybody can win. So the end users can see cheaper electricity, and they can make sure that any solar energy that is generated when they're not at home can be used by somebody locally or stored locally for their use later on. So we've shown that all of the technology can be sort of deployed relatively easily. So these are just some of the challenges that we have to face to make these schemes work for real. Things needs to be licensed. To act as a distribution system operator, you need a license, and the cost of that license is very, very prohibitive at the moment. Smart meters need to be employed in all houses, and that is slowly happening in the UK. We need to have access to the capacity market at lower battery sizes. We need local motivation to get communities involved to invest in this. And we need big communities, so we need to scale up the community sizes to get the most cost-effective use of them. We need the DNOs to drive the infrastructure investment in this. So they need to understand that they get a benefit from using energy communities. And then we have to exploit all the up and coming technologies. So electric vehicles provide opportunities for incorporating vehicle to grid. The Internet of Things and all of the associated software challenges with that are ideal for enabling energy communities. And investment, money is needed to put these things together, and investors are looking on returns of investment within 2 years these days. So there's some real challenges in terms of getting money associated with this. And we're going out and publicising our results. So this is a day that we had in Parliament a few years ago, whereby this panel, including myself here, was specifically trying to convey the benefits of community energy as a way forward for our national infrastructure for electricity as well. So coming to some conclusions here, these proposed community control strategies can significantly improve consumer energy costs. They can reduce the power peaks seen by the network operators. They can virtually eliminate reverse energy flow and the protection problems associated with that. And they can help us to expand the network to incorporate electric vehicles, heat pumps, and any other electrification of loading systems as well. So therefore, the proposed controllers are of benefit to both the network operators and end users. You know, it's what they call a win-win situation. And end users seem happy to accept these new technologies. They seem happy to work with them as long as they can see a benefit from using them. I mean, the biggest disadvantage, I guess, is that the financial support for the system, the investments in the equipment required for the system is quite large. And we need to change some of the regulations that we have within how electricity networks operate to allow these things to operate for real in a legal fashion. But those are not unsurmountable. And as I say, we're doing work to try and push back some of these barriers as well. And in the UK, I think we're seeing more and more of these community energy systems actually operating for real as well, which is very encouraging, which is good to see. So I think that's my presentation. So I'm happy to take any questions if I can.
Thank you, Mark, for your presentation. Now, if you have any question, please raise your hand and you can present your questions. Miguel.
Okay, thank you, Claudio. Thank you, Mark, for the presentation. As you mentioned in your conclusions, there is a big challenge or barrier in terms of financial support for the implementation of these systems. And but in terms of the technical implementation, what do you think will be the biggest challenges in terms of the control, the modeling, for example?
I think at the moment, the biggest challenge probably is security. Because I mean, I guess a well-developed system, we have reliable power electronics these days, and control systems are well known, whether they're model predictive control, heuristic, or whether it's, you know, artificial intelligence or anything like that. But I think the biggest concern with people who were to get involved with this would be the cybersecurity aspect to it. So it's making sure that the data that's coming out of your smart meter is well protected, so that people can't see your consumption patterns and then work out when you're out of the house, that sort of thing. So from a purely technical point of view, I think it's more looking at software and communication side. As I said in my conclusions, I think the real biggest challenges are to do with getting network operators to accept that these systems can be operated stably. So as an academic, we do proof of concept things, and I guess it's up to real network operating engineers to actually look at the fine detail here and try and predict where potentially technical weaknesses might be, and try and engineer around that. And I guess that is in terms of just making sure that the control is robust in terms of control algorithm itself, but in terms of what happens if there's a short-term communication failure, which means that the system has to operate autonomously at a local level for a short period of time. But I think things like the power electronics, the batteries, the PV systems, they're all mature. There will be developments in these to make them better and cheaper and, you know, more power intensive. But they're at a stage now where they can be sort of confidently deployed within houses, because they are at the moment on an individual basis, I guess. Does that answer your question?
Sure. Yeah. Thank you. Yeah.
More questions? Please, if you have any question, raise your hand. Marco, go for it.
Okay, thank you very much for your presentation, Mark. A very interesting topic. As well, I'm not expert in your area, but I'm wondering how well prepared is the people in the community to adapt themselves to the implementation of this kind of new technologies, in terms of culture, or in terms of conscience of the environment, so on.
That's a really good question. So we had some social scientists involved with two of the projects who really were interested in that sort of question. And I guess the communities that we got involved with were almost self-selecting. They wanted to be at the forefront of a new technology. They wanted to be involved with something that could make a difference environmentally. I mean, that's how we sold it, because that's what we believe. So the people who were participating in the original projects were very, very keen. But when it comes to things that directly involves them on a day-to-day basis, like demand-side management, that was quite interesting, because for the first few weeks or months of the project, they would happily do whatever we were asking them to do in terms of delaying using a washing machine or delaying using a dishwasher. But then gradually, as time progressed, the number of times they overrode our actions. So we would say, don't turn on yet, but they would still switch on. the number of times that the overriding was done started to increase. And I guess we got to, you know, we went from a place where we probably had 90% acceptance for demand side, for load shifting applications, 90% acceptance, maybe to 50%. And I guess once, you know, you have to run projects for longer than that, maybe, to see what the final settling value is. And then you can build that into your management algorithms as well, you know, to assume you're not going to have 100% compliance, but maybe 50% compliance. And I guess the other thing really is trying to really focus, when it's load shifting, on things that do not interfere with what a customer actually wants to do. So shifting heating or shifting air conditioning for 15 minutes is acceptable. You don't notice too much difference in that, and that can make a difference to your energy management. So that would be a priority. Moving of electric vehicle charging certainly is something that is relatively easy to do as well. So I think maybe once we understand fully what sort of technologies are involved with electric vehicles, for example, and how that settles down in terms of vehicle to grid, or whether it's just something that we can use as a load shift, then we can start to prioritize different things in terms of load shifting, so that we put the least amount of decision making on the end user. But sort of coming back to your question, I think most people, if not all, were very enthusiastic to start with. And even towards the end of the projects, they were enthusiastic. It's just that their enthusiasm to allow you to take over their washing machine had dropped off a little bit. Does that answer your question?
Yes, thank you very much, Mark. But I have just one more question in the same topic. Have you been involved in any project or any experience related to the same area, but with the people in the rural communities? Because I'm living in a rural community, and most of the people there is afraid. They don't really believe, or they don't really want to update the technology in their houses, because they don't know, they don't have the experience, they don't have the education for that. But you say that most of the people agree and very happy with this implementation. But in the other side, in the rural community, what about your experience on that?
Yeah, so most of the projects, certainly the projects I've described in this presentation, were city-based communities. Yes. And I understand that that's different, but we've done some work with installers who install in the rural areas of Nottingham. So there is a lot of equipment going out there, and bizarrely, one of the reasons is for rural people to have some control over their power and have less reliance on the national grid or the national distribution system. You're right that they don't necessarily want to work in communities at the moment, but we'll maybe go back and address that when we've got chance to, by showing them the results of what happens within the cities. To be honest, I can't answer your question directly, because I've not really tried to do energy communities in a rural environment. We're just sort of trying to get the technology into individuals in a rural environment. We've done that a little bit. So I guess that's a challenge for us to do, hopefully in the near future, is to see if we can create a rural energy community. Because I think once you can demonstrate it working in one community, then you can maybe start to spread the message.
Yeah. Okay, thank you very much, Mark.
Thank you, Marco. More questions? Mark, I would like to ask two points. The first one is the results that you show us consider, or what technology of battery consider? Lead acid, lithium ion?
Oh no, it's all lithium ion. If I can just go back to pictures, find them. Yeah, so in these houses, this is a lithium-ion battery. It's just 2 kilowatt hours, relatively small, but still able to do a useful job.
So in that case, what is your opinion about the battery technology? What is the best option for this kind of technology?
Well, I mean, with us, because these were funded projects, we were able to invest in lithium, and it was lithium phosphate, I think it was. So that's a relatively safe lithium technology that people were happy to have in their garage or in their house. So I mean, this is a lithium phosphate battery, and these are smaller versions.
Yeah.
And this one as well. And I think these technologies are okay. And potentially, if you're looking at energy communities, what you would do would be to not use brand new batteries like this, but you would create a community battery out of second life electric vehicles. It's a perfect use for that technology. So if you think that for a community you need 3.5 kilowatt hours for an ideal battery capacity, then something like a 25 kilowatt hour battery coming out of an electric vehicle would serve what, 8 houses. So it provides quite a substantial amount of energy there for what would be a relatively low cost. And we've seen from other people's projects that you can get a good lifetime for a stationary application for an electric vehicle battery, up to 10 years. So potentially the economics of investing in that technology are very, very good. And I guess if you're trying to use that technology over the next 10 years to make use of second life electric vehicle batteries, what we're then doing is buying time to find a better battery technology that's cheaper or less reliant on rare mineral resources like lithium. So I don't think there's any one particular ideal solution at the moment, but there's almost a roadmap to get you to where you want to be in 10, 15 years time, hopefully.
Yeah, okay, thank you. Thank you. Miguel, do you have another question?
Yes, just one quick question. Looking at the picture there, I wonder whether you use real PV panels or you emulate the panels in that installation.
No, they're real. I'm sorry, I don't have a picture of them, but they're real. They're outside. They're outside the laboratory.
Okay, great.
And they've worked very hard this summer because we've had a lot of sun in the UK this summer. I think they've been a bit of a shock to the system for them, unfortunately.
Yeah, for sure. How was the temperature in?
Well, we got up to 40 degrees. Was it 2 weeks ago? Yeah, which is unusual. There's a big joke in the UK that we had a very good summer in 1976, and this is equaling it. So if you're old like I am, you can remember the previous heat wave we had.
Okay, thank you.
Okay, I think that is all. Thank you, Mark, for your presentation. Thank you to the attenders, and see you in the next seminar. Maybe it's going to be at the beginning of September. So thank you again, Mark, and thank you for your time and for your interesting presentation.
Okay, well, thanks very much for inviting me today. Thank you, Claudia.
Okay, bye-bye.
Bye.
Thank you, bye.
Thank you, bye-bye.